I'm the guy who was just telling that story you were listening to. So I want to talk about reciprocity, and reciprocity sort of makes sense. If you're a true number theorist, you just care because you hear about, like, oh, squares mod p. That sounds like an interesting question. But if not, you know, and I assume there's some non-number theory people in here. I mean, you might wonder how we got to the point where we actually cared about that. Right? In antiquity, there were just the integers and then the rational numbers, and then slowly we developed other things like algebraic things and the real numbers and the complex numbers, and people got really, really freaked out every time we did that and thought that there was like witchcraft going on. There's an apocryphal story that the man who proved that the square root of 2 was irrational was actually keel-hauled and killed because this was heresy, that there were irrational numbers. And this was done by the Pythagorean cult. I'm pretty sure this is just apocryphal, but you never know. But, you know, so this all sort of started with some basic ideas. A long time ago, we figured out how to solve ax plus b equals by equals c. First of all, that's an ordinary line, right? But if I want to solve it in the integers, there's a way to know all of the solutions if you can find even one. And there's a way to know whether or not there is one solution, too. So this is a very well understood problem and one we can deal with fairly simply. Similarly, something like y equals x squared plus ax squared plus bx plus c is also fairly simple to solve using something like the quadratic formula and testing to see if things are integers or not. Right? So these two classical problems were well solved, and the first, what I would call interesting or moderately challenging problem that you don't learn about in, say, high school algebra was something we call Pell's equation, which looks like x squared minus dy squared equals n. Right? So here it's understood that we're looking for integer solutions. So numbers like 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, 0 sometimes, but nothing like the square root of 2. Or in particular, I can't pick the square root of n minus d times 0 squared, right? I mean, that's silly. That's too easy. So by adding this restriction on, we get things get a lot harder, right? Now, for one thing, I want to make some reductions here. This is way too hard to solve just as is. So first of all, I'm going to assume that there are no squares that divide. This long symbol means divides d. Right? Not divide, right? And because why not? Because if d has squares, I'll just absorb them into y, right? Because if x, y is a solution, then say d equals L squared times m, then x comma Ly is a solution to x squared minus my squared equals n. Right? So I can absorb squares into y. Right? Because if I take one integer, multiplying by another one keeps it an integer solution. So d has no squares in it, okay? This will turn out to be very interesting. Now, what about the problem with n, right? Well, if n has any squares in it, right, if n equals L squared times m, then if I can find a solution for m, right, say x squared minus dy squared equals m is solvable. Then if I use Lx squared minus dly squared, that's n, because that's m times L squared, right? I just multiplied both sides of the equation by L squared. Right? So in particular, I can go down to the case m has no squares in it too. All right, fair enough. I'm making some progress. Here I'm going to use a very, very nice identity. It's almost like magic. And I want to use difference of squares. X plus y square root of d, x minus y square root of d. This isn't the magic one, right? You guys all know this is x squared minus dy squared. Right? You learn difference of squares in calculus, and you do it like 1,000,000 times to calculate the same limits, right? Pedro knows about that. We did that last semester. Yeah. Well, the students certainly help, right? That's not last semester, a couple semesters ago. Wow, it's been a while, hasn't it, Pedro? Yeah, I know, right? It was last spring, I think. All right, I TA'd for him at one point. He's cool. All right, so now what I want to note is that x plus y root d times z plus t root d is xz plus dty plus xt plus yz root d. Right, so this, if I multiply two things of this form, I get another thing of this form. In particular, if I do the same thing with the minus signs on the other side, I find that xz plus dty squared minus xt plus yz squared times, let me put the d in front like I have been. Have I been putting d in front? Yeah, d in front. This is equal to the product of whatever these two difference of squares was. So in particular, if I can solve this for prime numbers, oops, sorry. I'm giving a talk in the math room, and I'm late if that alarm goes off and I'm not there. So in any case, we have this minus that. If I could solve, say, the first one, x squared minus dy squared is some prime number, and the second one, z squared minus dt squared is another prime number, then this whole thing is equal to p times q. Right? And I can then pick up even more prime factors. Right? If I can keep on solving things that look like this for more primes, then I can get any square-free integer, right? And that means I can get anything because I reduce down to the square-free case. So if I can manage this for primes, I'm really golden. I can do this for anything then, right? So it now remains to say, okay, what happens when I'm dealing with prime numbers, right? The sort of basic building blocks of all number theory. All right. Well, the first thing I want to note is that equality is really a ridiculous thing to ask for at the beginning, because if I had actual equality for a prime number, I'd be golden. But sometimes it's hard to find the way that things work with equality. But we have tools in number theory to deal with divisibility, right? So if I can get something for a prime, then certainly I should get something divisible by that prime, right? So if x squared minus dy squared equals a prime, then certainly the prime divides x squared minus dy squared. Right? So if I could rule out the possibility of this being divisible by p, then certainly I can never have equality, right? Any number that's not every number is divisible by itself. If this isn't divisible by p, then it's never equal to p. So now we're getting into an interesting state of affairs here. Maybe I'm not demanding this, but I'm demanding x squared minus dy squared equals pk, right? Some multiple of p, and I want to see if this is even possible, right? This has a lot more machinery associated to it, so it's an easier question to answer. All right. So first of all, let's demand that p doesn't divide x and p doesn't divide y, right? Because if so, then I have x equals pj, y equals pi, and I have p squared times j squared minus di squared, right? And if that's true, then I'm definitely not going to be equal to p. I want this to be divisible by p. But if it's really divisible by p, like p squared there, then again there's no hope, right? You can't have this as equal to p, because if I divide both sides by p, I get 1 is divisible by p, which is crazy, right? All right, so we're going to assume that x and y aren't divisible by p, just so this is not really silly. Okay. We've made some progress here. We started with a really big equation, and now we're down to a bunch of square-free things, and one of them is only a prime. Yeah, what's up?
Dumb question. This is okay even if one of x or y is... So then again... So if...
Yeah, no, you only need one of these. I'm just sort of shuffling on the table.
Oh, I see. Okay.
Right, because if this is divisible by p, and this is divisible by p, well then dy squared must be divisible by p.
Yeah.
So you're going to prove that y is, basically. So now I want to use a fact. So I really don't want d to be composite, even though it's square free. I want it to be a prime. So I want to use the following black box fact, which is not hard if you know some general theory, but if you don't, which I suspect most of you don't, it take a while to prove. This works for, say, d equals p1, p2 up through pk. So this is square free, so these are all different primes, right? If and only if the number of pi so that x squared minus pi y squared doesn't work. In other words, that this is not divisible by our favorite prime p, is even. Doesn't matter how many ones that do work are in D, as long as there is an even number of ones that don't work. Okay? So I'm just going to black box that because it's, I mean, it's nice, but it's not the point of the talk. Basically, I'm doing this because I want to reduce down to only worrying about individual primes, right? Because this thing here now looks like x squared minus dy squared, where the d is a prime number. Right? Now I have two prime numbers, and those two I'm going to be able to work against one another so that if I know one thing about one of them, I can find out about the other one. Right? I'm bootstrapping up, which is sort of the entire philosophy of mathematics. Right? I don't know enough stuff, so I'm going to break it into really small pieces that I understand and then build a big thing out of those pieces. All right, so the only other fact I'll need to black box for now, and this you could actually prove yourselves if you worked at it a little bit. If p doesn't divide y, which is our assumption, right, then there exist integers a and b so that ap plus b squared y squared equals 1. Okay. So this is sort of a general fact about numbers which are called coprime to one another. What's up, Pedro?
It's not divided.
Oh yeah, sorry. Thank you. That's certainly not true if that does divide. Right? So, in particular, now I'm down to, so now in particular, that tells me that if I'm looking at x squared minus q y squared, right, I can write then, where am I? Oh yeah. So y isn't divisible by p, so let me write this as, so this is equal to pk, right, this is a multiple of p. So multiply both sides by b, I get bx squared minus q b squared y squared equals pk b squared. Right? So this is bx squared minus q. We have this equality. So this is 1 minus ap equals pk b squared, so that I'm left with bx squared minus q equals p times kb squared plus a. Right? And all this just means another p times some number L, right? So now I'm really talking about squares minus q being divisible by p. So that I could talk about x squared minus q equals pl rather than x squared minus q y squared. Right? I'm lowering the number of variables in another effort to simplify things. Right? This ability to move the divisible things over there is very nice because this gets rid of my extra variable problem here. Right, and then all I need is this magic fact here that I can write 1 in this special format. Okay? Is everyone cool with this so far? Any questions? Other than the black boxes. The facts, I'm just going to leave as facts. All right, cool. So now we're really cooking now because we're down to x squared minus q is divisible by p, which is very nice. All right, now we get into some more of the, we're going to get into some of the more modern theory. This is heavy motivation, but ultimately what we write for this is x squared is congruent to q modulo p. For those of you who have had some degree of number theory, you know that this literally means x squared minus q is divisible by p. I'm just restating the same thing in language that might be more familiar to some of you with that background. If not, you can just keep thinking of it as this divisibility statement, which is fine. because that's what it is. All right, for this, so now this is actually this is where we take a little foray. So Gauss had this genius idea. People had thought of this theorem before. Gauss was the first to prove it. The one I'm going to call quadratic reciprocity. It's a basic reciprocity law, the most basic for that matter. He had this genius idea that you could go outside of just ordinary integers in order to solve the problem, right? We did that a little bit earlier too, when we factored x minus root d times y, x plus root d times y. Guys, remember this uses real numbers because d is square free, so this definitely is not an integer, right? By going beyond the context you start with, you can prove things about your original context with greater ease. You don't have to do as much work, right? This is still true in the wider context of real numbers, but the fact that we're picking actual x and y as integers still keeps us within the realm of the question we originally asked. So what does that mean here? Well, Gauss realized that the heart, the real true heart of the matter of solving this kind of question actually goes all the way up into the realm of complex numbers. Right here, he decided to use a number, zeta p, which is what's called a primitive p-th root of unity. Many of you have probably seen this. If you haven't, I can tell you that it's a number that has the property that x to the p minus 1 equals 0. In other words, its a p-th power is 1, but it's also not equal to 1. Obviously, 1 works, right? 1 to the. And if you have any experience with Euler's formula, right, you know that e to the 2 pi I over p is such an object as far as the complex numbers are concerned. And there are many ways to get more of them from this particular choice. But if you like, it's a root of the following polynomial. pp of x is x to the p minus 1 divided by x minus 1. Right? This is saying its p-th power is 1, but it is not equal to 1, right? Because then this isn't defined. And if you happen to know, this is x to the p minus 1 plus x to the p minus 2 plus x plus 1. Right, this is called the p-th cyclotomic polynomial. So now we have a bunch of we have a complex number in here. How are we going to utilize it? Right? How is this possibly going to tell us about this question here, which is the one we care about? Fair enough. Gauss did this in an old-fashioned way. I promised you a modern way, so I'm going to treat you to a modern interpretation of how we use this polynomial. He did a lot of work with sums that look like, zeta p to the a, and then figuring out that if you have some specific combination of these things, you can get out a special real number that you care, well, a special square root that you care about. That's a little bit technical, and ultimately it's very boring, right? That's one thing I really don't like, is anything in math that happens to be boring. So we're going to treat it to the idea that was the root of the right idea, the one that motivated something called Artin reciprocity, and which motivates a huge field of research today called the Langlands program. It's started with this idea here and utilizing these zeta p's in a very algebraic way, and has built an incredibly famous industry. There are huge swaths of mathematicians working on these problems even today, which started here at this. So, not this. Sorry, Gauss. What do you care about? Well, there's a set we call Zx, which, for those of you who haven't seen it, this is actually very simple. This is polynomials with integer coefficients. Right? So x squared plus 1 counts, but 1/2 x squared does not. Because this one has a 1 coefficient, a 0 coefficient, and a 1 coefficient. Those are all integers. And this one has a half, which is bad. Even if I were to add 1, right? Oh, look, 1's a nice integer coefficient. Yeah, but the other, 1/2 still doesn't work. Right? 2x squared plus 1 would work. That's okay. But not this one. Right? And so every time I put something inside a bracket next to z, it means polynomials with these coefficients, and this is the thing that is the polynomial for. So if I write I call z adjoined zeta p, this is the same thing, except now it's a0 plus a1 zeta p plus an zeta p to the n plus well, I guess this is the highest power here, right? This is a perfectly reasonable object, except now instead of a formal polynomial, you can actually physically add these things up to make a number if you wanted, right? So this one here, like you have a variable, and this one here, you just end up with a number when you add them all up. I feel like that's a fair assessment, right? We do that all the time, right? If you guys are given in an algebra class like f of x equals x squared plus 3x plus 2, sometimes they tell you find f of 0, right? And that means you just plug in. That's what I'm doing. I'm literally everywhere I am, I'm plugging into every polynomial, I'm plugging the same value. Okay. Why is this interesting? This is important because if you look at phi p, right, this is this polynomial over here, right? We said earlier that the zeta p's are the different roots of this. Now my question to you is, if the only part of the definition is that the pth power is 1, how can I tell two of them apart other than 1? 1's very special, right? If I multiply anything by 1, I get the thing back. That's 1's property. It's the thing that you multiply other stuff by if you don't want to get rid of it. But all this other stuff, all the other roots, right? I said zeta p is a root, but how can I tell which one I care about? I mean, if I'm willing to go to like the actual complex numbers, I could say this is the one with the smallest angle from the positive x-axis, right? If you look at them, they're points on the unit circle. They have angles. But algebraically, you cannot tell them apart. You have to use analysis, a notion of an angle or a distance or something like that, in order to distinguish different roots of unity. Since this is an algebraic, a number theoretic fact, we don't want to prejudice ourselves with that, right? You guys remember back when you were learning about complex numbers, one of the first things you learned was that I squared is minus 1. Remember this? Okay. Well, minus I squared is also minus 1, right? And what's the difference? I mean, someone tell me, how do you personally distinguish between I and minus I? Right, if I were to draw, say, the complex plane like this, there are 2 points, this one and this one. Which one is I? This one, right? Right? Why is this one on top? Yeah, exactly. We made a convention that one of them should be here and the other one should be there. Right? And this is, you can tell them apart in a picture like this because you have, again, this is exactly what I was talking about, the notion of angle. This one makes an angle of pi over 2. This one makes an angle of 3 pi over 2. Right? Because we always count counterclockwise, right? If you count clockwise, you can get out right now. Right? So in particular, right, as far as the algebra is concerned, these two roots are interchangeable, right? We made a choice that the one we gave the name I to should be this one. Right? But that's just a label, right? And I'm not into labels. Right, this is awesome. You got it. Right? So in particular, I want to note that if I have I and I cube it, I get minus I. If I have minus I and I cube it, I get I. So these two things functionally are related to one another, that I can get one from the other by raising it to a power. Right? This is true for all the zeta p's. In this case, how does the rule work? Well, for now, I want p to just be an odd prime because 2 is really, really weird. Like, you have no idea how strange 2 is by comparison to the others. But then if I have zeta p and I raise it to some power a, in this range, I get another one of the roots. And in fact, I get all of them for these choices here. And let me just pick one so I have all primitive roots. Right? There are p minus 1 choices here. For each choice you make, if I plug in a there, I get a different root. Right? In the case of I, the reason that it's weird is because I is a 4th root of unity, right? Which is not a prime root. So I choose 1 and 3 because these are the two odd numbers, the ones that are less than 4 but don't have any factors in common with 4. Because 2 is the only real factor of 4, right? You just have it twice. So those were the numbers 1 and 3. I to the 1 was I to the 3 was minus I. Here I can pick all of them, right? Because all the numbers less than p are coprime to it. That's what it means to be a prime number. It means you have no factors smaller than yourself. Except for 1, right? All right. And now this is where our connection is going to come in. right? Because if you look, what happens if I do zeta p to the, say, qp? Oh, no, I don't want to use q again. So what's your favorite letter? Whoever picks k. Excellent. To the kp plus r, or say 0 less than or equal to r less than or equal to p minus 1. Right? Then this is, by definition of how exponent rules work, right? Zeta p to the p to the k times zeta p to the r. Right? In particular, this is 1 to the k. Right? So ultimately, this thing is equal to zeta p to the r for some r in this range. Right? And if the number isn't 1, r isn't 0. And so it's one of these over here. It's one of the primitive ones like I was talking about before. So now we have a means of taking one thing and generating all of them. And it's important because, this is the kicker, right? Notice this number here. It's kp plus r. Right? Two numbers are the same if their difference, in other words, if I have another one like, k prime p prime plus r prime, sorry, not k prime p plus r prime. If these things give us the same thing, then k prime minus k p plus r prime minus r has to be equal to a multiple of p. Okay, so jp, right? But again, this just means that I have j minus k prime plus k, p equals r prime minus r. R prime minus r has size less than p, right? I'm subtracting two numbers in this range, guaranteed their size is less than p, which means that if there's going to be a multiple of p, it better be 0. In other words, r prime equals r. So that's the beautiful thing about this, is that up here in the exponents, we get this divisibility by p relationship involved. Okay, so now we go back to our quadratic reciprocity questions. Right? If I'm there, what do I do in that? Well, I notice then all numbers by division, right? Q is equal to k, so let me put k sub q, so we show that this k depends on whatever q is, times p plus r. Right? Every number works this way. This is division. You learned this in like 3rd grade, maybe 4th grade, something like that. You've known this for a while, right? And you remember how you did rational numbers, right? Q over p is this integer plus remainder r. Right? Divide both sides by p. This is like, way off. Please tell me if you don't know this. Right? So let me get rid of the rational version. No, I like this version better. No denominators. So in particular, I want to talk about whether or not q differs from a square by a multiple of p. So that asks me if the remainder here is one which I can find from squaring something. Right? Whether or not that. And so this is completely determined by how this breakdown goes in terms of the exponent of zeta p. So now I've transferred the question from one additively to one that looks sort of multiplicative, right? I'm multiplying the zeta p's together to get a new number. And that just corresponds to adding their exponents because of basic algebraic exponent rules. All right, now we get to some crazy stuff here. All right. So now we have z with zeta p polynomials. If I give myself rational numbers, that's fine too. Right? This just means polynomial is now on the line rational. So for example, 1/2 x squared, 1/2 zeta p squared plus zeta p would work, but square root of 2 zeta p would be bad because that's not a rational number. Okay. And why do I care about this? This thing I care about because it has a property that it's a field. It's a thing where I can add things, multiply them, and I can divide by non-zero things. If I divide two elements in here, I get another one in here. With z, that's just not true, right? So that's the only reason why I move up to q. It's because here I can do that. There's a big branch of the theory of fields, especially ones over q, called Gauss theory. It's basically studying polynomials like this one, and usually this one's a very special case and everyone really cares about, that talks about how to do these symmetries of the roots, like I goes to I cubed, or zeta p goes to zeta p to the a. right? The things that generate other roots from your first roots is a study of symmetry of these things, except unlike symmetries of squares, which are like rotations and reflection across one of these axes, we're talking about symmetries of roots of a polynomial instead, right? Which if you want, you can think of as symmetries of a polygon, right? Because if I write the primitive p-th roots of unity, they're all, like around here, I connect the dots. I figure out how much to move my polygon around by, and that takes one root to somewhere else, and that determines where everything else goes. Right? So in a way, this is very geometric in nature. I'm just obscuring it because I want to focus mostly on the algebra. Right? So how do I deal with this? If I look at this field, this one is special because it contains a unique quadratic subfield. What does that mean? And it means this actually, let me move back over here. The unique quadratic subfield, by, again, some general theory, is going to be Q with the square root of P star. P star is just a special version of P. It's P, but possibly it's minus P. Again, I don't have time to indicate why P star is the critical thing there, but it's because it's the thing that's inside here. Right? I may have the square root of P in here. If P is, say, 5, for example, then 5 minus 1 over 2 is 2. So I have minus 1 squared, which is 1, times 5. So the square root of 5 is inside of there. But if P is 3, for example, I get 3 minus 1 over 2. So I get the square root of minus 3 is in there. Right? So I do P star because I know that this thing is inside of that thing. And this is the thing that's going to power our eventual result. So I want to care about this one. And we can translate it back. It's no worries. We can figure out the thing for P by using P star. OK. So let me label this. Where is it? Sigma A. Just so it's a function. And it's determined by the number A. Okay? What does this mean? So the trick is that sigma A leaves Q adjoined P star alone. In other words, if I do this to this field, it does absolutely nothing. Right? If I plug in A plus B square root of P star and do sigma, I shouldn't use A, B plus C square root of P star and do sigma A to this does absolutely nothing. This is just B plus C square root of P star again. Right? It's like the function f of x equals x squared. What does this do to the number 1? Right. It leaves it absolutely alone. It doesn't leave everything alone, right? Every other number goes to something else. Oh, sorry, for 0, right? But these two numbers stay there, right? So this thing here, we're talking about where the action is. If it does nothing to this special sub thing, that's going to be the trick, right? Corey's getting pizza. He didn't lose interest. All right. Now we're getting somewhere. This is sort of a big black box again. Just because I really wanted to give the modern standpoint. You guys can see a bunch of classical results till the day is done, right? But some of you have interest in learning like real math, and so you should see the motivation and how it works. All right. So now the trick here is that I should look at sigma q. Right? Why should I care about sigma q? Because if sigma q leaves this field alone, then that means q is a square. Right? The fact about squares is this number 2. Right? The numbers 1 less than or equal to a less than or equal to p minus 1. I can multiply them together and then reduce back down to the remainder. Let me put r again for remainder. right? If I multiply them together, I can go back using the remainder to get a number back in this range. So they're multiplicatively close. I can multiply them and get another result back in there, right? And in particular, p minus 1 has the magical fact that it's even, right? P is an odd prime. I said that earlier because I don't like 2 very much. At least not for the purposes of this talk. I love 2 in general. Don't tell 2 I said that. But right, p minus 1 is an even number, right? And the fact that this is an even thing tells us that the things to the second power are the things that leave this thing, this field, this set alone. Why is that? It's because this is a square root. There is, like I said earlier, remember the phrase unique quadratic subfield? It's the only degree 2 thing inside of here. And so it's forced to be the thing that is fixed by the sigma q that come, or the sigma a more generally, that come from squares. Okay, that's the thing. These number 2's match up. Only thing here of 2's has to do with the only thing in here. Half of these things are squares. It's the half of them that are squares that determine that. And so that's the key observation. That's the key connection. They're using a very, very deep and very important fact that there is only one thing in here, only one field in here that comes from a quadratic, that degree 2 things, remember? If there were other things, this whole theory would fall apart. Everything would come crashing down around us. We would weep and shut ourselves in our room and never do anything again. Or at least I would. Maybe you guys would get some popcorn and go to a movie. I don't know. But this uniqueness between these things connects the symmetries of this to solutions of this. Because if this thing instigates a square, then it fixes this. Okay, fair enough. So how do we put this into a useful format? This is a very nice from a theory point of view, because it connects something called, something. If you guys have ever had any group theory, this has to do with the fact that these groups are cyclic. Right? That's why there are unique subgroups of a specific order. How can we do this for computation purposes, right? That's the question. Because in life, it's nice to know that something is true from a sort of hand-wavy point of view, but ultimately you need to compute some actual things if you want to do any work. Right? And we wanted to find solutions to our original equation, and we've reduced it down to this thing. We should figure out if we could do this thing now, right? We've come too far to turn back now. Famous last words. Okay. I got this written twice, but I don't care, right? Somehow this is so important. All right, we're nearly there. Okay. So now here's really the kicker. We go back to z with zeta p. I had this thing, I should actually use it, right? I shouldn't just write it in a talk for no reason. If I look at the multiples of q in here, right? In the integers, the multiples of q are what? They are qk. K is an integer. Duh. What are the multiples of q in here? Well, they're qz. Z is there. Fair enough. Now I want to note something. Q is a prime number. What does that mean? Somebody tell me what does that mean to you, like in terms of like ordinary everyday things. Give me a hint. The word factor should be in there.
Doesn't have any vectors.
Right. It doesn't have any non-obvious factors. Right. Everything divides itself, and 1 divides everything. Right. If I'm only allowed to use integers, 5 is just 5 times 1, and I'm screwed. But again, say I give myself some new numbers, like roots of unity. Say I is what I'm willing to do, right? Well, then 5 is 2 plus I times 2 minus I, right? Difference of squares. This is 2 squared minus I squared, which is 5. Right? Suddenly I'm able to factor 5, right? And the head explodes. And the point is that if you allow yourself more numbers, your factorizations can change, right? Okay, why does this matter? Well, because in Q, up here, if I look at the number q, it's going to factor somewhat. It might actually not. It might stay prime. Like for example, if I allow myself I, then I still can't get 3 stays prime. I can't factor 3 because if I have a plus bi, a minus bi equals 3, then a squared plus b squared equals 3, and that's impossible, right? Either if I want this to be less than 3, then these numbers have to be 0 or 1, and I can't add 1 squared and 1 squared to make 3, right? So 3 stays prime, 5 doesn't. But it shows that something could happen up here. And indeed, we know that this thing does factor somehow into something we call ideal numbers. So this is actually really outdated technology. They're not really numbers per se, but it factors in a way that we can measure. Right? It factors into, say, k factors. There might only be one. This might stay q. Right? That happens. That definitely happens. But the multiples of q, but q basically factors like this, ideally, in this setting. Again, you should think of these as sort of like soft numbers in a way. And the kicker here is, remember the evenness from before was critical here, right? So now the question here is, if I look at these sigmas, right? The sigma a's that permute like the zeta p's, right? Zeta p goes to zeta p to the a. Then what it's going to do is it's actually going to move these things around too. It permutes all of these things, right? And now here's the kicker, right? If this thing fixes the quadratic or even numbered subfield, then in particular there have to be an even number of these things to make that work, right? Because somehow if I look at it as a square of something else, if it fixes the q there, then it has to like take half of them and move it to the other half. But if there's no halves, then you can't switch two halves, right? There aren't two halves to switch. So it turns out that, again, this is a mild black box because I want to get to the motivation. Sigma q fixes, again, doesn't mess with q square root of p star is equivalent to k is even. Okay, so let me put that in a little box. And now we can state a computational version of quadratic reciprocity. You're probably all thinking, I don't know how that's going to be, but it's going to happen. All right, so if I'm going to define the symbol QP equals, this is for convenience sake, it's an easy way to measure. 1 if q equals x squared mod p, minus 1 if q is not equal to x squared. In other words, either I have a square plus a multiple of p equals q, or I don't. Then I know that this is 1 if and only if k is even. That's what I just said here. But then I also know that k is even if and only if this is 1. Right? Because that's what I was saying over here. The action up on this thing happens depending upon p star when I look modulo q. In this case, this is my q. When I said modulo, like this q here has to do with those ideal numbers over there, q. So I can connect this one's behavior as a square to this one's behavior as a square. Because you guys ever seen, raise your hands, how many of you have seen modular arithmetic? Fantastic. All right, good. Right, so you guys know what happens when I do like z mod q, right? Like I take the things and I look at their remainders. I can do the same thing over here. I take z zeta p modulo this bigger version of q, right? And then the behavior here is exactly the same as square root of p star modulo regular q. That's why that's the thing here. I can do modular arithmetic without just using regular primes. I can use these idealized primes. Right? And that's how I get the connection here, because if this thing is a square, that means that k is even, because x minus the square root of p star, x plus the square root of p star is the factorization modulo this ideal q. Right? But then in particular, there are two of these, and all of these q's come from exactly one of these two, and there are the same number above this one as there are above, so if again, this is a smaller object. In there I have at most 2 square roots. This one and that one. If there are 2, then when I go up to the big object, where is it? Q zeta p, then there's exactly the same number above this one as are above this one. And that means the number is even, which is what we cared about earlier, right? And this is how you connect these 2 bits there, because 2 roots modulo this q is equivalent to, this is even. We did earlier, this is equivalent to, this thing is a square modulo p. So then, if you have if and only if and another if and only if, you just forget about the middle step, right, and just pretend like you knew these 2 were equivalent in the first place. And how do I write that in a way which is computational? Again, for the purposes of actually doing something with it, I write QP equals P star Q. Now you may say, how does that help me compute, right? Remember, this is either a number plus or minus 1. So say I pick 2 numbers, some big prime numbers like 23 and 59. Right? All right, well, 23, 59 is equal to, well, 59 is equal to, let's see, so I want minus 1 to the 59 minus 1 over 2 times 59. 59 minus 1 is 58, divided by 2 is 29. That's an odd number, so I get minus 59, right? This is equal to minus 59, 23, right? Now, this is really hard, right? I have to square a lot of things. Like there's 58 choices for me to square here, right? Experimentally. But here, look at this. This thing, I can remember how I can replace this number with its remainder. So this looks like, so 59 looks like minus 2 times 23, right? That's negative 46. Minus another 13, right? So if I have negative 59, or sorry, this is negative 59, right? Right? So then this number is equal to the number, where is it? Minus 13 over 23. Suddenly my numbers are smaller. Right? Now what? Right, now I'm like, okay, so I'm a little bit better, but how do I get any closer to this stuff? Well, at this point I go up here, I'm like, all right, now I need to compute this number. That's really hard looking. So what do? Again, so one fact about this is minus 1 to the 23 minus 1 over 2 times 13, 23. Every time you have a minus 1, you just pull it out by raising it to the, this is not a denominator, right? This is not a fraction. But this number minus 1 over 2, 22 over 2 is 11, so this is minus 13, 23. Again, this is really hard. I don't want to do this. So, because I'm really, really lazy. You don't understand exactly how epically lazy I am. So this is equal to minus 23 star over 13. Again, 23 star is minus, it's minus 23, so this is minus 23 over 13. Again, I did all this theoretical work. It should tell me something, right? Well then, what's this? Well, minus 23 is equal to minus 2 times 13 plus, this is minus 26. I need to add 3 to it. So this is minus 3 over 13. Right, again, this is still like 13. You might say, okay, I could just brute force it and figure it out. But again, I'm really, really lazy. So this is minus 13 star over 3. Fantastic, right? Well, now 13 star is minus 1 to the 13 minus 1 over 2. That's 12 over 2, 6, even number. So this is equal to minus 13 over 3, which is minus, and I can reduce this one. This 13 is 4 times 3 plus 1, right? So this is 1 over 3. Is 1 a square?
Yes.
Perfect, right? So this number here, in this symbol, which tells me whether or not things are squares, is 1. And there's a big minus sign in front of it, so the whole thing is minus 1. So I go back here and I'm like, okay, I could have wasted my time squaring numbers below 59 a lot of times and then reducing them down every single time to see if one of them was 23 off of a multiple of 59. But my incredible laziness allowed me to determine that I would have wasted my time, right? Because you'd have to go through and check them all, and that would take you a long time. Here I'm just like, nope, no chance. End of game. Right? And this is exactly how you use the law in general, right? The general theoretical framework is very nice because it relates understandings of factorizations of numbers to these bigger field things where you can use complex numbers like the square root of p star, which might be the square root of a negative number, right? And you can use zeta p, which is definitely a complex number, but you can use the exponents to figure out that the behavior here modulo one another is exactly related to the big framework. And the number theorists really care about the theoretical framework, but sometimes if you're doing something like, again, like in cryptography or something else like that, you might want to know if something's a square ahead of time, and this is just immensely gratifying to compute. You can do this with higher things. There's cubic reciprocity and and other higher notions of this, which sort of culminate in Artin reciprocity. But the idea behind it is just so ingenious that, like, ultimately this can simplify your life a very great deal if you're trying to solve your original equation, because this can give you a yes or no answer, right? And that's the really cool part about it there. Every time you do this, you just keep on reducing things down until you understand exactly what's going on there, right? And again, like if I wanted to, so in particular, right? Let me just tie this back to my original question. X squared minus, let's see, my original one was 59, so 59y squared equals 23. Is this solvable? No, because I can't even find something that's a multiple of 23 that works. Right? So if I were ever doing this, unlike, and again, maybe even then you're willing to like compute all these things because there's only 59 cases and you have computers. But this would take you infinitely many tries. Right? You could not do this by hand. You would have to keep on trying, and you would keep on failing forever, and your whole life would feel wasted. But instead, you can just save yourself some time and say, I'm not going to try and solve this because I cannot solve this. Right? And in particular, that means that if I want x squared minus 59y squared equals, say, 23 times, 23 times any other things, any other n's, right, that have 23 as a factor, but there's like an odd number of factors that are non-solutions, you can't solve those either. Or that you can solve those. They give you ways of figuring out how to solve them after that. Right? So this is a very computationally effective for those of you who care about things like computer modeling and things like that. And for those of you who care about the theory, there was the other stuff I said in the talk. Right? But so the moral of the story is, math's great, be lazy. All right, that's all I got. I'll also take questions if anyone has any. Because Corey's not here to say. Oh, yes, he is. Corey's here to say, please. If there's questions, if we have any. That's him doing my advisor's voice. All right, meeting adjourned. Pizza!